see the DMA controller 8257, and my name is Dr. Sumant Kadwane. There are various data transfer schemes, and among these schemes we have a parallel data transfer. The advantage of parallel data transfer or serial data transfer is data is transferred quickly, but it can be transferred only at small distances. So there are among this parallel data transfer, programmed input output and interrupt driven, but both these requires intervention of microprocessor, particularly accumulator in data transfer. So there is another method that is known as direct memory access, which is a method which will be shortly explained to you in the forthcoming time. Now, why there is necessity of this DMA controller? Let us consider we have a particular memory and we want to transfer the data from memory to the output device. The output device may be floppy disk drive. So each byte of the data is first transferred to the microprocessor, and through microprocessor it is transferred to the output device. And this introduces some wait states. If we want to directly transfer the data from memory to the output device without intervention of microprocessor, there is one controller which we called as direct memory access controller, and that is what is the necessity of this DMA controller. Now, what are the connections that are required in the DMA operation? In DMA operation, we have two pins in microprocessor. The name of the pins are hold and HLDA. Address lines A0 to A15 need to be connected. Data lines D0 to D7 need to be connected. In addition to that, memory read, memory write, and input output read, input output write, they have to be connected to 8257 with hold request, hold acknowledge, and there could be some memory which is connected to the address lines, data lines, and control signals like memory read, memory write, and input output devices which is connected to the data lines and read write commands. And 8257 is connected through DMA request and DMA acknowledge. So we'll see how it basically functions. Before that, we'll understand what is the pin diagram of 8255. So 8255 pin diagram has the following pins: D0 to D7 data bus, A0 to A7 address bus, input output read, input output write, memory read, memory write, clock input, reset input, ready, hold request, hold acknowledge, address enable, address stop, terminal count, mark, DMA request inputs for 4 channels, DRQ0 to DRQ3, DMA acknowledge output, DAQ0 to DA3 for the 4 channels, and chip select, VCC, and ground. And these are as per the pin diagrams that is shown in front of you. So this is nothing but the 8257 DMA controller, which is a 40 pin IC. Now this is the functional diagram of the DMA controller. So input output read, input output write, memory read, memory write, address strobe, address enable, chip select, ready. These are all the control pins. Thereafter reset, clock, VCC, ground, and terminal count, mark, hold acknowledge, hold request, DMA acknowledge, and this is all what is functionally shown for the address pins. Now let us understand the internal architecture of the 8257. So 8257 DMA controller basically has 4 channels: channel 0, channel 1, channel 2, and channel 3. Each channel is associated with a 16-bit address counter, and we are going to see the format of that. But it is having one input, that is DMA request, and another output, that is DMA acknowledge. So each of these four channel has the DMA request and DMA acknowledge. In addition to that, there is a priority resolver, so channels can be having their own priority, and we can have the cyclic priority also. So there is a priority resolver, and there is a control and logic mode set register. So these are the control signals A4 to A7. Thereafter ready, hold request, hold acknowledge, memory read, memory write, address enable, address stroke, terminal count and mark. These are connected to the control and logic. And read write logic, so A0 to A3 and reset clock, input output read, input write, output write, which are active low signals. They are connected to the read write logic block. And there is a data bus buffer, which in turn will be connected to the data bus D0 to D7, and all these blocks are connected through the internal bus. So this is what is the internal diagram of 8257. Now let us understand the operation of this DMA controller. Now this is our CPU, and there is an address latch in order to demultiplex the data bus and address bus, and there are certain control bus signals like input output read, input output write, and there is a memory. Okay, so conventionally the memory is connected to the CPU through the address bus, data bus and control bus. Now when the DMA controller is coming into the picture, it is because the peripheral device want to exchange data directly with the memory without intervention of CPU. So before the memory is connected to the peripheral device directly, the operation of DMA controller is known as slave mode. In this slave mode, the peripheral device will request DMA request DREQ to the DMA controller. The DMA controller in turn will request what we call it as a hold request to the microprocessor. Microprocessor, by completing its own instruction cycle, will acknowledge the DMA hold request. So it will acknowledge the hold signal to the DMA, and DMA in turn will acknowledge it to the peripheral device. So DMA request, hold acknowledge and DMA acknowledge. So after this, the address bus and data bus, which was priorly connected to the CPU from memory, is now connected through DMA controller to the data bus and control bus of the peripheral device. And in this way, the DMA controller will now move from what we call it as master mode from the slave mode, and now the memory will directly transfer its data to the peripheral device without intervention of CPU. So there are certain important registers associated with the DMA controller. One of them is terminal count register. The terminal count register format is like this. Bit D0 to bit D13 represents a 14-bit count, and basically some number is loaded into this particular terminal count register, and when the memory is being transferred, in that case the number goes on reducing and the maximum bytes that can be transferred through DMA, one channel of the DMA is 16 KB, because 16 is 2 to the power 14, that is 2 to the power 4 into 2 to the power 10, that is 16 KB. So 16 KB of maximum bytes can be transferred because of this terminal count register. But the remaining two bytes D14 and D15, they are reserved for certain operation. If they are 00, it stands the verified data cycle. If it is 01, then it stands for DMA write cycle. If it is 10, it stands for read DMA cycle. And if D15 and D14 they are 11, it is illegal. The DMA won't accept this particular digits. There is another register. The purpose of the register is to enable or disable the channel of the DMA controllers. So that particular register is called as mode set register. So this is the format of mode set register. Bit D0. If it is 1, it enables channel 0. If it is 0, it will not enable the channel 0. Similarly, if bit D1 is 1, it enables channel 1. If D2 is 1, it enables channel 2. If D3 is 1, it enables channel 3. If D4 is 1, in that case it enables the rotating priority that we are going to see further. If D5 is 1, it enables extended write. If D6 is 1, it enables the terminal count stop. If D7 is 1, it enables the auto load function. That is only available for channel 2, not for remaining channels. Now, priority assignment. Now we can assign the channels the priority. For example, if channel 0 is served, then channel 1 will be having the next priority. So if channel 0 is having highest priority, the next priority is for channel 1, thereafter channel 2, thereafter channel 3. So channel 0, if it is served, then channel 1 is having the highest priority. But we can also enable the cyclic priority. That is cyclic priority, that if channel 1 is served, channel 2 is having highest priority, then in the next operation channel 3 will be having highest priority, and the cyclic priority will be served like this. Channel 0 in this, if it is served, just served, then channel 1 is having the highest priority. Next priority is, if channel 1 is served, channel 2 will be having this priority, and it will be like a cycle. That is why it is called as cyclic priority. Now address inputs. Now what are the register accessed? It depends on the lower order address A0 to A3, internal flip-flop, and the status of chip select logic. So when chip select logic is 0, then and then only the registers can be accessed for DMA. So if A3 to A0 are all 0 and internal flip-flop is 0, then lower order byte of the DMA address for channel 0 is accessed. If it is internal flip-flop is 1, then the higher order byte of DMA address channel 0 is accessed. If A0 is 1 and all other bits are 0, then the lower order byte of terminal count register for channel 0 is accessed. If A0 is 1 and internal flip-flop is 1, then higher order byte of the counts of terminal count register channel 0 is selected. Accordingly, if A1 is 1 and internal flip-flop is 0, lower order byte of DMA address channel 1 is accessed. If A1 is 1 and internal flip-flop is 1, then the higher order byte of DMA channel address is selected, and accordingly it is true for channel 1, channel 2, channel 3 and for mode set register, if A0 is 1 and remaining all are 0, then mode set register is selected, which is write only, and status register, if A0 is 1 and this internal flip-flop is 1, then the status of mode register, which is read only, can be accessed. The various registers have to be first initialized and then DMA operation will be started. The steps to be followed for DMA operation of 8257 in master mode after its initialization are given below. The input-output device sends a DMA request signal when it is ready to the data transfer. 8257 holds the DMA request high to the processor, it then enables the particular channel. In response to HRQ signal, the processor will turn down the system buses into the next cycle and will hold a hold acknowledge signal to 8257. In response to this HLDA signal from microprocessor, the DMA controller will generate DMA acknowledge, which is the active low, through its control logic block as an acknowledgement to the requesting peripheral. At the same time, 8257 enables the address lines A0 to A7. These address lines becomes the output lines. The lower order byte of the memory location is placed on these lines. The address strobe signal goes high when address enable is high and places a higher byte of memory location on the address bus A8 to A15. The data transfer continues till the terminal count is reached. Now let us understand the interfacing of 8257 chip with the 8085. Now this is the 8257 chip and 8085 A0 to A3 are connected to A0 to A3 of the DMA controller. Now let us consider that the channel A address register is having the hex address as 60H. So 60H stands for 0110 and these are 0000. So A4 to A7 are 0110. So A4 is 0, that is why we are showing a bubble over here, and A7 is 0, that is why bubble over here, and these are not 0, A5 and A6, that is why we are not showing bubble. They are 1 1, and if the address is 60H, that is this is 0 and this is 0110, in that case only the chip select logic will be enabled or chip will be selected. Okay, so of course this A0 to A3 will change with respect to the channels, but for 8257 chip select, this A4 to A7 lines which are used for the chip select logic. Now similarly the DMA channel, we have shown the interfacing of channel 0 DMA register, that is address 60H. So channel 0 count register address will be 61, DMA address register will be 62, channel 1 count register address will be 63, channel 2 DMA address register 64, channel 2 count register channel 2 count register will be 63 and so on. The status register gives us the status of terminal count channel 0, channel 1, channel 2 and channel 3. So if it is D0 is 0, in that case the terminal count for channel 0 is reached. Similarly, if D1 is 1, then terminal count status for channel 1 is reached, and if all terminal counts are reached, in that case bit D4 flag update will be 1. So this is one of the circuit that 8257 is being interfaced to 8085, and there is some logic to generate the control signals, and there is a 3 to 8 decoder to select the chip select, and ABC are used to connect the address lines, and IO M bar will be connected to G1, and 8257 and 8085 as shown earlier, they are connected to the memory, and there is some input output device which is connected through DMA request and DMA acknowledge. Now let us consider one example that initialize 8257 DMA controller to transfer 2k bytes of data stored in memory locations starting from 2101H to the floppy disk connected to channel 1 of 8257. Assume that the address of the mode set register is 78H. The addresses of the DMA address register for channel 1 and terminal count register are 72H and 73H respectively. So first of all, we have to see that this bit D1 for mode set register is 1, it enables the channel 1, and bit D6 for the mode set register is 1, it enables the terminal count stop. That is why the address mode set register value will be 42H. Let us consider the terminal count register value. Now we want to transfer 2k, so 2k is nothing but 2 to the power 1 into 2 to the power 10, so that is nothing but 11. So bit D0 to bit D10 will be all 1. 11 number of bits will be 1, and here we are using 10, so 10 stands for the memory read operation. Okay, so the format for terminal count register will come out to be 87FF. Okay, so we'll be loading 87FF into the terminal count register in order to transfer 2k bytes of stored data in memory location. Now, so here it is already shown the format for mode set register. We want to enable channel 1 and we want to enable the terminal count stop. That is why it is 42H. Now for initialization of 8257, following steps are to be followed. First is load mode word into the mode set register, load the counts to terminal count register with lower order byte, that is least significant byte first and then most significant byte. Load the starting address of the memory location from where the data is to be transferred to the floppy disk drive to the DMA address register. The initialization program is as follows. MVI A, 42, it will load the control word into the mode set register which we have determined earlier into accumulator first, and 78 is nothing but the address of the terminal count register. So first we have to load it into accumulator, then out 78 means it will be loaded into terminal count register. Then we have to load the least significant byte of the count into the terminal count register. We have decided it as FF because the overall number was 87FF. So FF will move to A, then we will load it to the address of terminal count register which is 73H given in the problem. Move A, 87, that is nothing but the most significant byte, that we will be loading into 73H itself because this is the way we program the 16-bit terminal count register, by loading the least significant byte first then most significant byte. Thereafter we will clear the accumulator contents and we will transfer it to 72H which is the address of DMA address register, and then we will load 21 into accumulator and once again will it transfer to the address of DMA address register. So first we are loading the least significant byte, so 2100 is the starting address, that is what we have loaded into the DMA address register, and this is how we can do the initialization of 8257. So thank you very much. Here I acknowledge my teacher and guide Dr. P.T. Karule sir, who make me understand the subject and contributed me a lot. Secondly, the book by D.K. Kaushik, An Introduction to Microprocessor 8085 by Dhanpat Rai Publishing Company, and book by Ramesh Gaokar, Microprocessor Architecture, Programming and Applications by Mendran Publications, and of course the Google search